Okay, so section 7.4, integration of rational functions by partial fractions. All right, so first let me provide a little table here of some of the integrals, some of the straightforward integrals that we should be able to do already. Where all the way back here where we just have some of the rules of integration. Right? So a constant can be kind of pulled out of the integral, constant times the integral of the function, right? So some of these are classics by now. But these are the ones where we can just go to this table and know that the integral of cosecant squared dx is equal to negative cotangent x plus a constant. Good. And then some of these are ones that we're kind of just now developing. So now they're instant classics. Now that we've figured them out. But so as we develop more and more techniques for integration, we run into some usual patterns, and then we can kind of put those into a standard table that we can refer to if we need to. Okay. All right. So in this section, we're going to focus on the following idea. So remember, let's do a little review thing here. So let's go off to the side. So back to adding fractions. Good old adding fractions. Whoa, I don't know what that was. If we had something of the form of, say, a over x plus 1 over a plus 1, and we wanted to add these two fractions, we need a common denominator. So we're going to have to multiply this fraction by a plus 1 over a plus 1. And then we have to multiply this fraction, x over x, like that. And then we would end up with a plus 1 plus x all over the product of the two, x times a plus 1, like that. Like that, right? Okay, so now if we wanted to integrate this ugly looking fraction, x plus a plus 1, just moving out the x out in front, all over x times a plus 1 dx, then it would be nice if we knew how to break this ugly thing down, right? This looks really ugly. And in fact, it might even be even uglier if we distribute that x. So maybe it's presented to us as x plus a plus 1 ax plus x dx, right? We might be asked to integrate this ugly thing. Well, as we saw that, the way we started, these two, I guess I should have put them up here, ax plus 1 over a plus 1, the summation of these two is what led to this. So, based on that, I can say that, well, okay, so this is the same thing as having the integral of 1 over x plus 1 over a plus 1 dx, which means we can separate this into two separate integrals. This is the same thing as the integral of 1 over x dx, easy, plus the integral of 1 over a plus 1 dx. And super easy, right? Because this, even though it looks kind of ugly, does not have a variable of integration x. This is just some constant. We can treat it as some constant. So this is just going to be x times this constant. Easy, right? And then this is going to be ln. So these two are easy integrals to find. This one looked kind of ugly. Now, really it's not as bad, but it just doesn't look very pretty, right? So that's the goal of this section. We're going to be faced with integrating a really ugly fraction where the numerator is a polynomial, the denominator is a polynomial, right? Those are called rational functions. So we're going to have the integral of a rational function, and in some cases it might be easy to use one of our prior techniques of like a u substitution or something. But in some cases they're really, really ugly rational functions. So it might benefit us to break up that fraction into the summation and subtraction of smaller fractions such that, with the goal being that the integration of each individual piece might be easier than the whole pie. Good? So now how do we take a really complicated statement, a really complicated rational fraction, and break it up into the summation or subtraction of smaller fractions? Well, that process is pretty hard on its own. You know, ignoring the integral and the calculus part of it, that's an algebra question that is pretty tough. So hopefully this won't be the first time you've seen this, because it gets pretty rough, right? So hopefully it's more of a review than an introduction. But if it is your very first rodeo with these, you can review your pre-calculus textbook, and hopefully you guys covered that and maybe it looks familiar. And also, if you look in my math YouTube channel, the Math 180 pre-calculus class, somewhere in there I cover partial fraction decomposition, which is what we're about to do, but just kind of in a more detailed kind of manner, which this is just going to be more of a crash course into it. Okay, so let's say we have this fraction and this fraction, right? Two separate fractions. We subtract them. We need a common denominator. The common denominator is going to be to multiply numerator and denominator of this fraction by this. So we'll have a x plus 2 times 2. And then we got to multiply the numerator and denominator of this fraction by this. So we'll end up with an x minus 1 in the numerator. Of course, we have to do the same thing to the denominator, x plus 2. Let's multiply the denominator by the same thing. We get an x minus 1 in there. Okay, and so that's how we get this fraction right in here, right? So that's kind of messy, but that's how you get it. So let me just get rid of those things. Okay, so that's how we end up with this. And now we distribute combined like terms, and we end up with this guy. So just like I did over there, the point is that now if we want to integrate this ugly thing, right, we have the integral of this nasty thing. That's pretty ugly. And there might be another technique out there that works, like maybe we could do a u substitution, or maybe we can separate this in a variety of ways and somehow make it work, perhaps. So we're not representing that this is the only way to do it, or even that this is the easiest way to do it. This is just a way to do it. So one way to do it is to figure out how to reverse this process, how to go backwards from here to change this rational function into the difference of these two, which we do here. And then we have two separate integrals, which are each pretty easy. The integral of this guy minus the integral of that guy, right? And in both cases, we end up having to use the ln function. So it's ln of absolute value of x minus 1, and there's that constant there. And then minus, and then ln of x plus 2, plus a constant. Good. So it turns into a pretty easy integral. The hard part is figuring out how to do that, how to go backwards between the two. So really that's the heart of this section, is refreshing your memory on how to do that, how to separate them. Any questions so far? Sort of at least on the concept of what we're going to do? No. Okay, to be able to do that, to be able to reverse the process of adding or subtracting fractions so that we can express one complicated rational function as the addition or subtraction of smaller, simpler fractions, that process takes us all the way back to the fundamental theorem of algebra. Again, hopefully you've ran into that in your pre-calculus class. So we'll be sort of referencing it, but hopefully it won't be too bad. So if we have some function f of x, which is defined as a giant fraction where the numerator itself is a polynomial and the denominator itself is a polynomial, right? So some sort of rational function. It is possible to express f as a sum of simpler fractions provided that the degree of p is less than the degree of q, such that the rational fraction is called improper. So first of all, we're going to only focus on cases where the numerator has a degree that's less than the degree of the denominator. If that's not the case, then we can just do polynomial division to simplify it first, and then we'll end up with the case where the degree of the numerator is less than the degree of the denominator. Good? So at this point, when they're looking at proper fractions, they're looking at examples that look like this. Right? So for example, it could be that f of x is equal to, I don't know, how about x to the third power plus 2x minus 7 divided by x to the fifth power minus 2x squared minus 2, for example. Right? This is just a random example of what this could look like. Right? So it's a rational function where the numerator is some big, ugly polynomial, another polynomial in the denominator, and we want to find a way to represent this, to separate this into the addition or subtraction of smaller, simpler fractions, so with the goal being that hopefully once we break it up, it'll be easier to integrate it. Good? Good. Okay, so that's what this is saying, identifying what a proper fraction is. So an improper fraction, an improper rational function, would be an example where the degree of the numerator is bigger. So like, let's say we had this plus 2x squared plus 7x plus 9 divided by 3x to the fourth power minus 3x plus 2. This is just another random example. And here, the point is that the degree of the numerator is larger than the degree of the denominator, the polynomial in the denominator, so this is an improper function, an improper rational function. Good? So if we run into this, we're going to have to first do the polynomial division and then do the process we're about to do. Good. Okay, so if we define a polynomial in this form, right, any polynomial can fit this form, where the degree of the polynomial is equal to the power of the largest term, right, in this case is n, and then the coefficients are these guys, a sub n minus 1, a sub n minus 2, all the way out to a sub nx plus a sub naught. Right, so all of these a's are coefficients, and the variable of interest is x. Right, so there's a polynomial in the variable x that is degree n. Good. So if f is an improper function such that the degree of p is greater than the degree of q, then we must first take the preliminary step of dividing them. Right, so use polynomial long division to divide them. And the remainder r of x is obtained such that the degree of the remainder is less than the degree of the divisor, q. Good. Questions? No? So once we divide them, then we can write any fraction, right? Any rational function can be expressed this way, where we have some sort of a polynomial there, some sort of a polynomial, plus, and then the remainder over the divisor. Good. That's all this is saying. So either we will run into fractions like this, where the degree is smaller than the denominator, or we might run into fractions where the degree is larger than or equal to the denominator. And in cases like that, divide it first, you'll end up with some sort of polynomial. So f of x will then be written as some sort of polynomial of x plus, and then there will be the divisor over here, 3x to the fourth minus 3x plus 2, and some sort of remainder function. This remainder function will be less than degree 4. So it might have remainder of degree 3, remainder of degree 2, remainder of degree 1, or maybe just a constant. Good? Okay, and then some other polynomial that goes there once we actually divide them. Good. Questions? Okay, so here's our first example. Let's say we are asked to deal with this integral. The integral of x to the third power plus x, all of it divided by x minus 1. Okay, so notice that this is a case or an example where we have an improper rational function here. The degree of the numerator is larger than the degree of the denominator. So we have that x to the third power plus x over x plus 1, minus 1, minus 1. And so the degree of the polynomial in the numerator is 3, and the degree of the polynomial in the denominator is a 1, right? Sort of this invisible 1 there. And that looks ugly. Is 1. Good. So this is an improper fraction, so we're going to have to do division. All right, so let's refresh our memories on how to do that. We got x minus 1, and we're going to do this, and we're going to end up with x to the third power. Now remember, when you do this kind of division, you have to include all the powers. So because there is no x squared, we have to throw it in there, and the way we do it is by introducing a 0 in front. 0x squared. Good. And then we go back to plus 1 plus x. So power of 3, power of 2, power of 1, and then we also introduce another 0 out here, plus 0. So all of the powers are represented in descending order. Power of 3, power of 2, power of 1, power of 0. Here, same thing, they have to be represented, but this one only started with degree 1, so degree 1 and then degree 0. So there, they're all there. Good. Okay, next we got to multiply, we have to find something such that the multiplication of this term times this first term is identical to this one. Good. So we have to introduce an x squared there. X squared times x gives you x to the third power. X squared minus times negative 1 gives you minus 1x squared. Good? Okay, then we subtract them. If you want to subtract them, that's fine, but it gets a little confusing with all the minuses and the subtractions and all that running around. So what I like to think of instead is that I'm going to distribute a negative 1 and then add down. To me, that makes more sense. So I distribute a negative 1, making it minus x squared. Right? Since these two were identical, when I distribute a negative 1, they're always going to be the opposite sign. And so therefore these cancel. When I distribute a negative 1, I'll get a plus 1, and then I add down, so I'll get a positive x squared. Good. Good. Okay. Then I bring down the next term, which is an x to the power of 1. And I go back up here. So now, again, I got to multiply blank times this term equals exactly that term, including the sign, which is positive in this case. So let's put a plus x there. That gives you x times x gives you x squared minus x. Good. X times negative 1 is minus x. Again, I think about distributing a negative 1 and then adding down. So when I do that, that first term cancels. Minus 1 makes it plus x, so this gives me 2x. Good. Bringing down the last term, which is just plus 0. Good. And now if I multiply plus 2, 2 times x gives you 2x. 2 times minus 1 gives you minus 2. And once again, distributing a minus 1 and then adding down, we'll cancel that term, makes that a positive 2. So all those pluses and minuses running around can get a little tricky. Okay, so all of this tells me that this original fraction, which was x to the third power plus x over x minus 1, right? This rational function can be expressed as x squared plus x plus 2 plus 2 as the remainder over the divisor, which was x minus 1. Good. Any questions? Questions? Good. Okay, so now we can go back to our calculus question over here. So we have this integral of x to the third power plus x over x minus 1 dx. And we go, okay, well that looks kind of ugly. Instead, let me say that instead of doing that question, I'd rather answer this question. X to the second power plus x plus 2 plus 2 over x minus 1, the whole thing multiplied by dx. And now this is just several easy antiderivatives, right? So this one is going to be equal to x to the third 1/3, and that will get me that guy, plus this is going to be 1/2 x squared, that'll give me that one, plus that guy is just going to be 2x, good, plus, and this will be 2 times ln absolute value of x minus 1. Good, plus a constant. Any questions, any questions, any questions? No? No, 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 no? Okay, and just to match it up with that statement from above, we had, we were given that if we have p of x over q of x, that can be written this way, plus some remainder of x over q of x. Right, so in this little scenario here, this is that polynomial s of x. The remainder turned out to be 2. The divisor is x minus 1, and so it fits this form. Good. Wait. Yeah, let's write it out, right? 2x, yeah. Okay. All right. The next step is to factor the denominator, q of x is possible. So it can be shown that a polynomial q can be factored as a product of linear factors of the form ax plus b plus irreducible quadratic factors of the form ax squared plus bx plus c, where b squared minus 4ac is less than 0. Okay, so this is saying, this is going back to the fundamental theorem of algebra, which says that if we have a polynomial, that we can break it down and factor it into terms that fit a linear profile like this, or maybe at least one or more quadratic ones, right? So if we have something to the power of 3, the power of 4, power of 5, we can break it down even more, right? We can further break that down. Good. So the properties of the fundamental theorem of fundamental theorem of algebra are what going to allow us to factor the q of x, the denominator of the rational functions we're going to work with, all the way down until we get all the way down to either linear equations like these, x minus 2, x plus 2, right? These are linear. Note that this fits the form ax plus b, right? Where the b is a 2 and the a is a 1, right? So this, negative 2. The b is a negative 2, and the 1, the invisible 1, is an a. So this is linear, right? So power of 1, linear. Same thing with this one. This is also linear, where this is going to be ax plus b, where the b is positive 2 and the a is still positive 1, right? So these are both linear. And then we have a quadratic. Right? This one fits the form ax squared plus bx plus c, where, okay, there is no bx, right? There is no term x. That means the b is 0. The a is a 1, right? And right in front of the x squared, there's this sort of invisible 1. A equals to 1. And the c equals to 4. Good. Good, good, good. Okay, so if we tried to break this one even further, we would find that the answer is imaginary. If the answer wasn't imaginary, we could break it down even further and end up with more linear factors. Now, when we're doing it by hand, we often, most math books provide cases or focus on cases where these things are constants, easy to work with values, especially if you're not using technology. But really, it could be an ugly decimal or a fraction here. It doesn't have to be a whole number. And so, if you're able to use the quadratic formula, you can, and then that might lead to a further breaking it down even further into linear products. Good. Does that make sense? Good, 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 good. Maybe, kind of, sort of. Again, you can revisit your fundamental theorem of algebra from pre-calculus. Okay, so we're going to be given some sort of a rational function. We're going to factor the denominator as much as we can, and then we're going to use partial fraction decomposition to separate it into the addition of fractions or subtraction of different fractions. And we're going to use the patterns that are sort of suggested in order to be able to do that. And so these are the two kinds of fractions that we're going to be using when we break down our rational function. It's going to be a summation or subtraction of fractions of this form, or addition or subtraction of fractions of this form. So the denominators are all going to be equivalent to the terms of our denominator once it gets factored. Did you have a question, or you just have a open mic? Questions?
Oh, sorry, that's my fault. No, I need it.
Oh, okay, cool, no problem. All right, so the first thing we have to do is look at our denominator and break it up into distinct linear factors. Well, case one is that when we factor the denominator, we're going to run into a long list of distinct linear factors. So they're linear and they're all unique. They're all different from each other. If that's the case, then it turns out that what we need to do is rewrite it in this format, where each one of the factors in the denominator gets its own fraction, and there's a constant up in the numerator. Right? So I know this can look a little confusing if it's, again, I hope it's not the first time you've seen this, but just to explain, let's say that I start off with some sort of fraction, some sort of rational function that looks like this. X to the power of 2 plus x plus 7. And let's say that there's an ugly polynomial here. Ugly poly. I'm not even going to write it down. I'm just going to say it's some sort of an ugly polynomial function here. But after I factor it, let's say I'm able to factor it, let's say that that polynomial factors into x minus 2, x plus 3, x minus 1, I don't know, something like that. Maybe there's a constant here, 3, something like that. Sorry. Okay, so let's say that it factors into this. These are distinct linear factors, right? They're linear and they're all different, right? There's no repeats. And then we keep the same denominator, x to the second power plus x plus 7. Okay, so what this is telling us that in order to break this fraction down, we're going to have, this third out here can just be separated. And let's just put that out here. Right? We just factor out the 1/3. And then we're going to have one fraction that has an x minus 2 plus another fraction that has an x plus 3 plus another fraction that has an x minus 1. right? So when we factor it like this and they all look different and they're all linear, then we end up with 3 different fractions. And now there's going to be constants up here. Capital A, capital B, capital C. Constants that we need to figure out, right? So that will be our mission. And that's really the hard part, finding these constants. Well, actually, they used a sub 1, a sub 2, a sub whatever, dot, 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 all the way out to a sub k. But I could just use capital A, capital B, capital C, right? So these are constants that need to be determined. Capital A, capital B, capital C are constants that need to be determined. Right? But at least we have the general setup of what it's going to look like. Is that okay? Questions? Okay, so let's do an example that involves something along those lines. Okay, so let's say we want to evaluate this integral. So first of all, before I dive into integrating, I want to work with this thing off to the side. And the first thing I want to note is that this is a case where our rational function is already a proper rational function. The degree of the numerator is already smaller than the degree of the denominator. If it wasn't, then I'd have to do some division off the bat. But that's not the case here. Okay, so the next thing I want to do is look at that denominator, and I want to try and find a way to factor it. So I want to factor that guy. All right, so they all have an x in common. So let's go off to the side over here and factor 2x to the third power plus 3x squared minus 2x. So they all have an x in common, so let's factor that out. We end up with 2x to the second power plus 3x minus 2. Good. And now we end up with a quadratic. I could use the quadratic formula, but since the numbers are pretty small, this feels like a really good guess and check situation. So I'm going to guess and check, right? Guess and check. And there's not that much to guess. So the 2x squared makes me think one of the terms must have a 2x and the other term must have an x. Right? That's how you get 2x squared. And the fact that this is a 2, well, there's only a couple ways that can happen. Either there's a 1 here and there's a 2 there, right? That's going to give me a product that equals to 2. But I need it to be minus, so I need one of them to be a negative. So maybe this one's a minus and this one's a plus, or maybe the other way around, right? So I can play around with this in a couple of ways and then check to see if it works. So if this is the case, this would end up giving me 2x squared plus 4 minus 1, and that'll give us the 3 minus 2, right? So I just kind of stumbled into it. Good? Clear? Clear? It's a little bit luck, a little bit practice. If you foil this thing, and foil that thing, we end up with 2x squared plus 4x minus x minus 2, which gives me 2x squared plus 3x minus 2. Good, good, and that's what I wanted. If that didn't work out, if that didn't work out, then maybe I would try something different, right? Other things to try is to move around the terms this way. X over there, put a 2 there. Maybe put the minus there and the plus there. Try doing that, right? Switching those two. Or maybe switching around the constants. Maybe try 2x minus 2 times x plus 1. You know, move those around. I don't know, just make some moves. There's not too many options, not too much variability because the numbers are easy. And if none of that works, then maybe jump to the quadratic formula. And remember that it might be the case that the answer reaches into the imaginary numbers. Right? Remember the quadratic formula is negative b plus or minus the square root of b squared minus 4ac all over 2a. And if this term right in here is negative, if the b squared minus 4ac is negative, then we're looking at imaginary solutions. And if we're looking at imaginary solutions, that means stop. Leave it alone. Leave it as a quadratic. Good. Good. Okay, but in our case, it worked out well. We found out that this is how you factor the denominator. So far, we're on our way. We're definitely not done. We're long from being done, but the first big hurdle has been accomplished. We were able to represent the denominator as a product of x times 2x minus 1 times x plus 2. Good. So we have distinct linear factors. We have 3 linear factors here. So according to partial fraction decomposition, the suggestion is that if we have something like this, then this will break up into 3 different fractions. Where each one of these fractions has each one of these terms. Right? And this is only because they're all linear and because they're all unique. None of them are being repeated, meaning that they're to the power of 1. Right? Next, we'll look at a case where maybe one of these is repeated, like it's x plus 2 squared, or x plus 2 to the 3rd power. So if there's a power, one of these terms is repeated, then there's something else we have to do. Okay? All right, so now we have constants that we have to figure out. Right? If I can find the value of a, b, and c that goes there, there are special numbers, like maybe this is a 1, a 2, and a 7 or something, or a -1, a 2, and a -3. Who knows, right? That's what we have to figure out. So this is really what we need to solve at this point. Good. Any questions at all right now? Questions? Okay, well, I really should have given myself a little more room, so I'm just going to try and work this out over here. Okay, so I'm going to just copy it over here because I need the room. Just put it over here. Let's see, we need x to the 2nd power plus 2x minus 1 all over x times 2x minus 1 times x plus 2 is equal to some number a over x plus some number b over 2x minus 1 plus some number c over x plus 2. Okay, what we want to do is use the power of that equality. The left side equals the right-hand side. So I'm going to multiply both sides of the equal sign by x times 2x minus 1 times x plus 2. And as long as I do the same thing to the other side, multiply everything on the right-hand side by the product of x times 2x minus 1 times x plus 2. As long as I do the same thing to both sides, I maintain that equality. So that equal sign gets to come down. Now on the left-hand side, good things happen. All of these terms cancel with all of those terms. So the only thing that survives all that cancellation is the numerator of x squared plus 2x minus 1. On the right-hand side, I have to distribute this. So this gets multiplied, all 3 of them get multiplied by the first fraction. All 3 of them get multiplied by the second fraction. All 3 of them get multiplied by this last fraction. And for the purposes of making sure you can follow this first time, I'm going to actually write it all out. But then I probably won't do this step moving forward, since it's, I think, a pretty easy thing to imagine. So all 3 terms times that one, plus b over 2x minus 1 times, and then all 3 terms times this one, x, 2x minus 1, x plus 2, and then plus c over x plus 2, and then all 3 terms times this last one. 2x minus 1, x plus 2. Good. Okay, and lots of good stuff happens here because this cancels with that, and then this one cancels with that one, and this one cancels with that one. So what survives is x squared plus 2x minus 1 is equal to some constant value a times 2x minus 1 times x plus 2 plus b times x plus 2 plus c times 2x minus 1. Oh, there's an extra x there. X times 2x minus 1 times c. Okay, that's pretty ugly. We're going to go ahead and FOIL all of these out. So this is going to stay the same. X squared plus 2x minus 1 is equal to, so if we FOIL out the 2x minus 1 times x plus 2, so I'll end up with a times, and I get 2x squared. That makes it 4x minus x, makes it plus 3x minus 2, plus b times x squared plus 2x, plus c times 2x squared minus x. Good. X squared plus 2x minus 1 is equal to, now I'm going to distribute that a, so I get a times 2, let's put the 2 out here, 2x squared plus 3ax minus 2a plus bx squared plus 2bx plus 2cx squared minus cx. Okay? Alright, this is where it gets really tricky. What we really want to do now is regroup everything on the right-hand side by the terms that have the same powers. Good. So I'm going to put all the terms that have an x squared together. That has an x squared, that has an x squared, that has an x squared. I'm going to put together all the terms that just have an x to the power of 1. So this one, and that one, and that one. And then finally there'll be the term that doesn't have an x at all, and there's only one of them, that's this one. Okay, so let me just regroup them. I have 2ax squared plus bx squared plus 2cx squared. That's all the terms that have an x squared. Now plus, and I have 3ax plus 2bx minus cx, and then finally a minus 2a. Okay, and all of that is equal to the left-hand side, x minus 1. Okay, here's where the power of that equal sign really comes in. What I want to do is factor out the common terms to these three. They all have an x squared in common. These all have an x in common. And then this one doesn't have anything, leave it alone. Okay, so this is going to be equal to 2a plus b plus 2c parentheses x squared plus sorry, 3a plus 2b minus c, and all of that multiplied by x. And then there's this minus 2a over there equals, and then over here we have x squared plus 2x minus 1. Okay, so here's the geniosity of this thing. The balance of the left-hand side with the right-hand side must be maintained, right? So if we focus on the fact that my computer's not working, okay, so the x squared term, on the left-hand side, I have a 1. 1 times x squared. That lets me conclude that all of this right here must be equal to 1, because it's the term in front of the x squared. So it's got to be equal to 1. And then the term in front of the x to the power of 1 is a 2. Right? So this part here is a 2. So that lets me conclude that this whole thing right here must be 2. It's the term in front of it. Good. And then finally, the term that doesn't have any x's at all, the constant, is -1, which makes me conclude that this must be -1. Good. So out of all of this mess, we can conclude the following system of equations. We can conclude that -1 must be equal to, well, let's put it the other way around. We can conclude that -2a is equal to -1. We can conclude that 3a plus 2b minus c is equal to 2. And we can conclude that 2a plus b plus 2c is equal to +1. Any questions so far? Remember, our goal is to find out the values of a, b, and c. Right, going back to up here, our goal is to find a way to represent this ugly rational function. Let's put it up here. We have this ugly rational function. We want to find a way to represent this as the addition or subtraction of simpler fractions. So we factored the denominator, we got it to this, and then by partial fraction decomposition techniques, it is suggested to us that this is the process. So we have to find the values of a, b, and c. And now, after all this work, we have a system of equations that will hopefully do that for us. Now the a is super easy, right? So I can just take from here, I can just say that -2a must be equal to -1. So a equals to -1 divided by 2. Okay. Questions? So I already have the value of a. That works. And then these two, I gotta find a way to solve them. To solve this system of equations. Well, okay, I already have the -2, so once I have the -2, I can plug them into here and simplify these things a little bit. So this is going to be 2b minus c is equal to 2 minus 3a, and from here I get that b plus 2c must be equal to 1 minus 2a, and I already know the value of a. Good. Okay, so if I can cancel out one of these letters, I'll be able to find the other one. Good. So let's, for example, multiply this one by 2, and then I'll end up with a 2 right here, and then when I add them down, I'll be able to get a 0. Right? So cancel out the c's. Okay, so I'm allowed to do that in the following way. I'm going to take this equation and I'm going to multiply everything, left side and right side. I'm going to multiply everything by 2. Multiply by 2. So if I do that, I end up with 4b minus 2c equals to 4 minus 6a. Multiply everything. Yes.
For the a, I think it's supposed to be positive 1/2. So
oh, thank you very much. Yes, so let's put that a plus there. So a equals to 1/2. Good thing I hadn't plugged it in yet. Okay, so let's make that a, yeah, thank you for letting me know. Right? These problems are long and ugly, and if you make a tiny little sign mistake somewhere, you could definitely go down the wrong path for a long time, and then it hurts. Okay, so that's why I left it there. Let's just pretend I was smart enough to know that that's why I left it there. So let's leave this. Oops. So then now I'm going to leave this bottom one alone and just rewrite it as b plus 2c equals 1 minus 2a. Good. And now I can add them. Right, so I'm going to add these two. And that gives me 5b. 5b. These guys cancel. 5b equals to these guys, which is going to be equal to 5 minus 8 capital A. So b equals to 5 minus 8 capital A over 5. And luckily, a is a simple value of a half, so that makes it easy to figure this out. So b is equal to 5 minus 8 times a half over 5. So let's stick that half in here. So b is going to be equal to 5 minus 4 over 5, which equals to 1/5. Good. So we have two of them down. We have b equals to 1/5. We have a equals to 1/2. And once we have those two, we can easily find the value of c. So let's just go back to over here. Say use that one. We have 3a. We have 3a plus 2b minus c equals to 2. And so 3 times a half plus 2 times 1/5 minus c equals to 2. So let's put a plus 2 minus 2 situation here. Let's add a plus c there, minus 2 minus 2. So this is going to be 3 over 2 plus 2 over 5 minus 2 equals to c. Let's multiply this numerator. Let's get a common denominator, right? So let's make it a 10. So that'll be 5 over 5 to get a 10, and a 2 over 2 to get a 10, and then a 10 over 10 to get a 10 in the denominator. So that gets us to 15 plus 4 minus 20 all over 10 equals to c. So that'll be negative 5 over negative 5 plus 4 should be equal to negative 1/10. Okay, that was ugly, painful. Any questions about any of this so far? Okay, so such a big, these problems are so big and nasty, it's easy to just completely get lost with what we're trying to do here. So let me try and get an overview shot of everything once again. So once again, the point is we started with this ugly rational function, and in order to integrate it, we need to figure out a way to separate this into the summation or difference of smaller, simpler fractions. We factor out the denominator, and that's how we got these terms. And the methods of partial fraction decomposition let us know that when we have unique linear factors down in the denominator, that means that each one of those terms becomes the denominator in its unique fraction, with constants up in the numerator that we have to solve for. So after working really hard, we found out the values of all those constants. It turns out that the a was actually equal to positive 1/2. Turns out that the b is actually equal to positive 1/5. It turns out that the c is minus 1/10. That's what I got. Minus 1/10. half, positive 1/5. Good. Okay, so after all this work, then we can conclude the following. Let's go over here and write down our integral one more time. So the integral of x squared plus 2x minus 1 all over 2x cubed, 2x cubed plus 3x squared minus 2x dx. Turns out that that whole thing is really equal to the integral of, and then we had 1/2 over x plus 1/5 over 2x plus 1, or minus 1, plus negative 1/10 over x plus 2. Dx. Right, and that's just coming from here. Right, minus 1/10 over x plus 2. Good. All right, so now instead of one big, ugly, nasty integral, we got 3 reasonable, manageable integrals, right? We can simplify this a little bit. Let's turn this into 1/2 integral of 1 over x dx plus 1/5 integral of 1 over 2x minus 1 dx plus, well, okay, let's just make that a minus 1/10 integral of 1 over x plus 2 dx. Good. So this would be equal to 1/2 ln of absolute value of x plus 1/5 ln of, and then we have absolute value of 2x minus 1, and then kind of guessing and checking, the derivative of this is 1 over this times the, using the chain rule, we'd have an extra term of 2, which we don't want, so we also have to introduce an extra term of 1/2. And so actually I should have put it out here. Let me put that in front. So this is 1/5, 1/5, and then I'm going to put the extra term of 1/2 out there to balance out with that chain rule. I don't like putting it out here because then it looks a little confusing. Some people might think that the 1/2 is inside the argument of the ln function. We don't want that mistake. And then minus 1/10, and then ln of absolute value of x plus 2. Good. Plus some constant. Any questions at all? Questions? No? Okay, let's see if that's what the author did. Factored it, same factors, right? They're linear factors, so we have a, b, c. Good. Multiply both sides by this denominator, and you end up with this. You FOIL out, combine like terms, and you end up with the same system of equations that I got. And then you end up with the same terms. Yep. So you end up with 1/2, 1/5, negative 1/10. Yep. And then, yep, you get the same thing. 1/2 ln x, absolute value of x, plus 1/10 ln of 2x minus 1 minus, yep, that looks exactly right. And that's it. Any questions?
I have a question.
Yeah.
So instead of foiling out everything, could you pick a value of x that can like zero out
Oh, yeah.
some of the, okay.
Yeah, that's another way to do this, and that kind of comes at what stage? Where are we? When you have it at this stage, when we have it like this, so we get to this stage, and then we multiply both sides of the equal sign by all of this. We can get rid of all these fractions, and we get to this. And so another common technique that you might have learned is to think about what values of x will give you a 0. So a convenient choice would be to make the x's equal to -2, right? And this is an equality, so whatever happens on the left-hand side must be equivalent to whatever happens on the right-hand side. So if we toss in x equals to -2, conveniently this thing becomes 0, and 0 times whatever this is, right? It doesn't even matter. Once we plug in a -2 there, we'll get -2 minus 1. This will become -5. But it doesn't matter because 0 times anything is 0. So this whole term disappears when x equals to -2. When x equals to -2, this whole term will also disappear. Right? If we let this guy be -2, then this whole term also disappears. And so we'll be left with -2 times 2 times -2 minus 1 times c. That kind of messy thing. So this is going to be -4 minus 1 becomes -5 times -2, times -2 c. So that gives you 10c on the right-hand side. And on the left-hand side, same thing. Plug in a -2 there, plug in a -2 there. We'll end up with 4, -2 squared is 4, minus 4, minus 1, so these guys cancel. So after all of this work, we end up with -1 equals 10c. Divide both sides by 10, and again we conclude that c must be equal to -1/10. So see, we got the same answer. So this method is another fantastic way of doing it. It just requires a little bit more creativity. You have to really kind of pay attention and figure out which values, give you a 0. And so it might take a little bit of guessing and checking. Maybe a 1 would work out, maybe a 0. So it's usually pretty easy to tell, right? So we need a 0 here. That'll give you a 0 there and a 0 there. And then 0, 0, we end up with a -1. Right, so let's try that one. If we have x squared plus 2x minus 1 is equal to a times 2x minus 1 times x plus 2, and then we have a plus b, x plus 2 plus cx, and then we have a 2x minus 1. Okay, so another fantastic choice is to let x equal to 0, and that's because if we let this be 0, then this whole term is going to become 0. Right? We'll end up with 0 times -1, which is 0. And if we let x's be 0, here we'll end up with a positive 2 times 0, so this whole term will go away. And then over on the left-hand side, we'll end up with 0 squared plus 2 times 0. So on the left-hand side, the result will be just -1 equals to a times 0 times 2, which is 0 minus 1, 0 plus 2, which is a 2. Okay. And so we end up with a equals to -2a, and so 1/2 equals to a. Another one, right? So 2 down, 1 to go. We just have to figure it out. So try different ones and figure it out. So just kind of based on your own prior math experience, you might be prone to one more than the other. So however you want to do it is fine. When the test comes around, I will accept anything as long as you show me the work. Right? The only thing I don't want is for someone to just magically show me what the answer is with no justification. Right? The exam is not an opportunity for you to tell me what the answers are. I know the answers. You need to prove to me that those are the answers. So If you want to do it this way, that's fine too. Just show me some work, show me what you plugged in and how you got, how you concluded that A had to be a 1/2 and it couldn't possibly be anything else but a 1/2. Questions? Yeah, we're good, 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 good. I think people are just kind of prone to like whatever they first saw. So if in your prior math experience you got to a matrix like this and then you needed to solve that matrix, then this is more comfortable. And if when you first saw this, you were taught to solve it by plugging in convenient choices of x, then that's fine too. The only thing about this system is that I think it's a little harder to solve it this way. I think it is probably a little easier to kind of conveniently choose values of x. The only reason I tend to lean toward this method is because it's another opportunity to work with a system of equations. And in your various math career or engineering or whatever it is you're going to be doing in school, I think it's often the case that you'll run into some sort of matrix that you need to solve. So it's just an opportunity to have practice with it. Also, if they get really ugly, then there are computer programs that just solve linear equations, right? You can just Google systems of equation calculator, and there's just equations systems out there. You just plug them in, and the whole thing gets solved. So there are, when they get really, really ugly, there are techniques out there that you can use. Good. Good. All right, moving on then. So here's another example. So we have the integral of x squared minus a squared, where a is not equal to 0. Okay, if there was an x already in the numerator somewhere, this would be a much easier question, right? Because then we can just easily do a u substitution where u equals to the denominator. Its derivative is going to be equal to 2x. So if we already had an x in there somewhere, it would be easier to solve by the substitution method. In the previous method, we looked at things that were similar to this one, where maybe there is a proper substitution of x, like x equals to a sine theta, might be a good guess. But if you note in the previous section, those all involve roots, the square root of x squared minus a squared. So the fact that the root's not there complicates life a little bit. So let's try it by this partial fraction decomposition. Again, I'm not suggesting it's the only way to do it or that it's even the easiest way to do it. It's just a way to do it, and we're practicing this method, so might as well try it out. Okay, so first of all, we want to factor this guy. So if we have x squared minus a squared, where a is definitely not equal to 0, that's a difference of squares. So this is going to be equal to a plus a times x minus a. Okay, that part's fairly easy. And they're linear, right? Linear term, and they're not identical, so they're distinct linear terms. Right? They're not the same. Okay, so then by our methods of partial fraction decomposition, we say that this is going to be equal to this which is equal to some fraction, which will have the x plus a in the denominator, plus some other fraction that will have the x minus the a in the denominator. And again, we're looking for some constant capital A, some constant capital B. Good. It's our mission to find those two. If I can find those two, I'll figure out how to separate this guy. Good, 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 good. All right, so just like before, I'm going to copy this down. I have 1 over x plus a, x minus a, is equal to capital A over x plus A plus capital B over x minus A. I'm going to multiply both sides of the equal sign by an x plus A times an x minus A, x plus A times an x minus A, and then distribute. When I distribute, I know that the x plus A is going to cancel, giving me just a term of A times x minus A. And when I distribute here, the x minus A terms will cancel, giving me a B times x plus A over there. And then everything cancels in the left-hand side, giving me just a capital 1. 1 equals to all that. Good. All right, so then I have 1 equals 2, and then I have AX minus, and this is ugly notation. I have capital A and lowercase a, but they're two different things. So here is a case, this is a situation where it's case sensitive, right? Maybe I should have used different letters, but I'm not that bright. BX plus A capital B. Good. Again, we're going to regroup them. And so when I regroup them, I'll have that 1 must be equal to A x plus bx. I'm just putting together all the terms that have an x, minus capital A lowercase a plus lowercase a capital B, like that. And then I'm going to factor out that x, so I have that A plus B x, and then this guy, just to have the positive term as the leading term, I'm going to just switch them around and say it's lowercase ab minus lowercase a capital A. Good. And then again, I rely on the power of that equality. Now, because there is no term over here new terms, if we want to, that have a 0 in them. Good. Okay, so based on that, I can see that the constant in front of the x must be 0, which means that this must be 0. Good. And I can see that the term that doesn't have an x is a positive 1, which means that this whole thing must be positive 1. So that's how I can conclude this matrix. A plus B must be 0. Okay. And at the same time, it must be true that A capital B minus A capital A must be 1. Good. Good. Okay, so from here I can conclude that A and B are additive inverses. They add up to 0, so it must mean that A is equal to negative B. They're almost the same value except they're opposite signs. Right? Okay, so I can substitute that into here and say that this is capital AB minus A, and then instead of capital A, I'm going to plug in this minus B. And that whole thing equals to 1. Minus minus gives you a plus, so this must be AB plus AB equals 1. So 2AB equals 1. So capital B must be equal to 1 over 2 lowercase a. Good. And now I can come back up here and say, well, then that means that A, which is equal to negative B, must be equal to negative 1 times B, which was 1 over 2A. Or just that A equals to negative 1 over 2A. Any questions? No? No? Okay. So let's go back to the big picture over here. Let's zoom out. So we started out with this thing here. We want to integrate it. We want to figure out how to break it up. We know that it separates into the summation of these two. And after a whole lot of work, we figured out that this guy right here must be equal to negative 1 over 2a, whereas this guy must be equal to 1 over 2a. All right, let's take that over here and work on our integral. So I'm just going to make some room over here. So I have the integral of x squared minus a squared. Well, remember, a is a constant. We have a 1 there, dx. Right? And this is where a does not equal to 0. Okay, so based on our work, we know that this is equal to the integral of negative 1 over 2a divided by x plus a plus 1 over 2a divided by x minus a. And the whole thing has our dx in there. And remembering that a is a constant, and it's not 29, it's a constant a, so maybe that's worrisome. So this is an a, this is an a, and this is an a, and this is an a. It's starting to look like a 29 to me. Okay, so remembering that these are all constants, they're not the variable x, so I can take this whole term and just put it out in front. So I'm going to rewrite this as negative 1 over 2a out there, integral of 1 over x plus a dx, plus 1 over 2a integral of 1 over x minus a dx. Good. Okay, so then this is going to be pretty easy now. This is going to be ln of absolute value of x plus a. Just kind of guess and check for a second, right? So the derivative of this is 1 over all of this, and that's exactly what we want there. That's good. There's no other constants or anything. And then plus 1 over 2a, and then ln of absolute value of x minus a. Good. We can probably simplify this just a little bit. Let's move these things around. So I'm going to factor out a 1 over 2a, and then I have a minus ln of absolute value of x plus a, plus ln of absolute value of x minus a. And then if I switch these things around, I'll end up with 1 over 2a bracket ln of x minus a minus ln of x plus a. Good. And remember that when we have a subtraction, right, there's a little rule for logs. If we have ln of a minus ln of b, right, we have the same logs and we have a subtraction. That means we can tuck them under one big happy log and rewrite them as log of a divided by b. Right, that's one of our properties. So we can just combine these two into one big happy log and say that this is going to be 1 over 2a times ln of absolute value of x over a, x plus a, in that order, minus plus a constant, and I think that's as good as it gets. Any questions? Questions? don't know. These are big problems, so I don't think I can even put the whole thing under one screenshot. Almost, but it's really messy. That's what I hate about these electronic boards. Do a much better job in a real board of keeping things neat and organized. Good, good. Questions? Okay, let's see what the author did over here. Oh, I don't know what the author did, but that's the answer. Yeah, okay, they match. Okay, integration of rational functions by parts. Let's see, what is this? Okay, this is pointing out the alternative method that we'd already kind of considered, where we can choose a particular value of x, a convenient value of x, that helps us achieve the results that we wanted. So we already talked about that. Okay, case 2. Case 2 is a case where the polynomial in the denominator of the rational function we're working with factors into linear factors that are in some cases repeated. So it has maybe like to the power of something. Good. So here is an example of what we're talking about. You're given some polynomial, and often it's already factored for you, just because that part can be really tricky. So many of your homework problems, you'll see that the denominator's already been factored. Okay, so but what we have here is we have a linear factor of x minus 1, but it's being repeated. It's being raised to the power of 3. And we have a linear factor of x, but it's being repeated. It's being raised to the power of 2. So when we deal with something where we have a linear factor being repeated, what we have to do is create a fraction for each, where the denominator has each of the powers starting at 1 and leading up to and stopping wherever power is observed in your polynomial, in your rational function. So because this is a 2, it means that we have to have a term with x to the first and then x to the second. Good. Because this is a 3, that means we have to have an x minus 1 to the power of 1, and then x minus 1 to the power of 2, and then x minus 1 to the power of 3. Right? So it's this count up from 1, 2, 3, all the way up to wherever that stops right there. Good. And then there are constants on the numerator of every one of those fractions. So it can get really, really ugly. Again, just to highlight this, if we had, on the other hand, 2x minus 1 raised to the power of 4, right? And then there's some polynomial up here. It doesn't really matter what this is. X squared plus 2x plus 7. And let's say we had x plus 1 to the power of 2. Okay, so this is suggesting that we should have one term that has x plus 1 to the power of 1 plus another fraction that has x plus 1 to the power of 2. And I stopped there because there's only 2 terms. And now this is the one that's going to be really painful. Since there are 4 of them, it's being repeated 4 times, I'm going to have 4 fractions. 1 fraction, 2 fractions, 3 fractions, 4 fractions, where I have to have this term, the 2x minus 1, the power of 1, 2x minus 1 to the power of 2, 2x minus 1 to the power of 3, and 2x minus 1 to the power of 4. Right? So that's how this breaks down, and there'll be constants all the way here. A, B, C, D, E, F, right? So we have to figure out all those constants. It's going to get ugly. No doubt about that. Questions? Okay, so let's look at this example. So the first thing we have to do is factor the denominator and see how bad things are going to get. So let's take that over to the side. We have x cubed minus, no, actually let me try working down here and doing it this way. X cubed minus x squared minus x plus 1. So there are 4 terms. My first thought is maybe do a factor by grouping, see if that works out. So if I factor out an x squared from those first 2, I get an x squared x minus 1 plus blank copy, right? That's how we do factor by grouping. I'm going to focus on the first 2 terms. I factored out an x squared, leaving me an x minus 1. Then I put a plus blank and then copy this term. I copy it right there. I don't even look at the last 2 terms yet because if factor by grouping is going to work, I need this term and this term to look identical. So now that I've done that, now I focus on the last 2 terms and I try and fill in this blank so that it works out. So that blank times this term equals the last 2 terms if it exists. If it doesn't, then maybe factor by grouping doesn't work. Okay, so now after looking at that, looks like negative 1 is going to work. Negative 1 times positive x gives you negative x. Negative 1 times negative 1 gives you positive 1. Good. Okay, next, these 2 terms are identical, so we can factor those out, x minus 1, and we have x squared times 1 plus negative 1. Right, so this one times this one equals that, and this one times this one equals that one. So then this turns into x minus 1, and then we have an x squared minus 1. Good? Okay, now this is a difference of squares. This factors even more. X minus 1, and then this turns into x minus 1 times x plus 1. Right? This is a difference of squares. That just comes back to, just put it in case you forgot. This is this. Whenever we have 2 binomials that look almost identical, but one has a plus, one has a minus, when we FOIL them, we're going to get this special property that the middle terms cancel out. And so we end up with a squared minus b squared. So that when we want to go backwards, if we see that we have something squared minus something squared, we know that this is how it factors. Right? So here I have something squared minus 1 squared, something squared minus something squared, a difference of squares. That's how you can right away notice that this is how it factors. X minus 1 times x plus 1. Good. And now these 2 are identical. So I can, again, simplify this as x minus 1 squared times x plus 1. Good, 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 good. Okay, so now that I managed to factor the denominator, I'm a little closer to finding my answer, but still long ways to go. 2x squared plus 4x plus 1 all over x cubed minus x squared minus x plus 1. Okay, so this, well, the numerator, we haven't done anything with the numerator, so let's leave that alone. Minus 2x squared plus 4x. Well, you know, before I factor it, let's point out that this is a higher degree than that. Good. So it's good that we factored it. We got that in our pocket, right? But I need to do polynomial long division to simplify this and then plug in the fact that I know how to factor that in order to get to my answer. Okay, so let's erase this thing for now. We'll come back to it. And let's go off and do some good old-fashioned polynomial long division. So we have x to the power of 3 minus x squared minus x plus 1. All of the powers are being represented in descending order. That's good. And that's going to go into x to the power of 4. And now the power of 3 is missing, so I got to toss that in there. Plus 0x cubed. minus 2x squared plus 4x plus 1. Okay, so now x times that one is going to give me x to the power of 4. Right? Make them look identical, including the sign. X times x cubed equals to x to the power of 4 minus x times x squared is going to be minus x cubed minus x squared plus x. Good. All right, so now distribute a negative 1 and add down. So distribute a negative 1 and then add them down. When I distribute a negative 1, this will be opposite signs. These guys cancel. Negative 1 makes it a positive x cubed. So adding it down, we get x cubed. And then plus makes it a minus 1x, so minus x squared. Minus gives you a plus 3x. Right? Bring down the plus 1. And now making them identical, I need this to be plus 1. 1 times x cubed is going to give me x cubed minus x squared minus x plus 1. Okay, so distribute a negative 1 and add down. Or if you just want to think about it as a subtraction, that's fine too. So these guys will cancel. Minus makes it a plus, and then adding down, that means these guys will cancel. Minus makes it a plus, which means I get a plus 4. So positive 4x, and then minus means that these two cancel out as well. So I just have 4x. And I know I'm done because now the degree of this is smaller than the degree of this thing. So I'm ready to express this ugly fraction. So back to the original fraction given. Because the degree of the numerator is larger than the degree of the polynomial in the denominator, I do long division, and now I see that it's equal to x plus 1 plus this fraction, 4x over x cubed minus x squared minus x plus 1. Good. Okay, and well, also we already know how to factor. We already factored this, so the whole thing is going to be equal to x plus 1 plus 4x over x minus 1 squared times x plus 1. Right? That's what we got over here when we factored the denominator. What's going on? Good. Pretty good. Okay, so now we got to work on this part of it right here. Got to figure out how to simplify that by itself. I know that this is going to end up being x plus 1 plus something, and I want to simplify that. Okay, so that's where we do partial fraction decomposition. We're going to end up with 4x over x minus 1 squared x plus 1. And based on the properties of partial fractions, we know that this is going to be one fraction that has an x minus 1 plus another fraction that has an x minus 1 squared plus another fraction that has an x plus 1. And all of these are going to have constants a, b, c. Good. I'm going to multiply both sides of the equal sign by this, the denominator, x squared times x plus 1. And then everything on this side by, again, the denominator, x minus 1 squared times x plus 1. Good. Right. So on the left-hand side, this is going to turn into just 4x equals, and then when I distribute, the x minus 1 is going to cancel with one of these x minus 1s, so I'll end up with an a times x minus 1 x plus 1 plus b x plus 1 plus c, and that'll be x minus 1 squared. Pretty ugly. Good. 4x is equal to, foiling this out, I end up with a times x squared minus 1 plus, well, this is just going to be bx plus b, plus c times, and this will be equal to x squared minus 2x plus 1 so 4x equals to ax squared minus a plus bx plus b plus cx squared minus 2cx plus c. Okay, again, we group them together based on powers of x. So we get 4x equals to a plus c x squared, and that takes care of this one, and it takes care of that one. And then plus, and then I'll have a b and a minus 2c x, and that takes care of this guy and this guy. Those are the ones that have a power of 1. And then finally I have the ones that are constants, minus a plus b plus c. Any questions so far? Make sure I'm not heading down the wrong path here. Come on. Okay, so come on. All right, so what we notice on this thing again is that the terms on the left-hand side are, some of those terms are missing, so I'm going to fill in the blanks. So I have that 0x squared, and then I have this positive plus 4x, and then I guess a plus 0, right, since it's missing. And then on the right-hand side, I have a plus c x squared plus b minus 2c x, and then I have a minus a plus b plus c. Okay, so we must conclude that the term in front of the x squared must be 0, so these guys must be 0, and that all these constants must be 0 as well, and that the term in front of the x to the power of 1 is a 4, so these guys must be 4. Good. So from all of that, I conclude the following system of equations. The a plus the c equals 0. The b minus 2c is equal to 4. And that negative a plus b plus c equals to Come on. Equals to 0. Okay, that's pretty ugly. Let's find a way to solve these guys. So first of all, I'm going to take these two, and if I cancel out the c, I'll end up with a new equation that has a and b in it. Good. And then if I take these two and cancel out the c, I'll have a new equation that also only has a and b in it, and I can solve it that way. Also, well, you know, this one's really easy to solve for either one and substitute. So I can solve for a and then have something that only has c's and b's in it. So let's do it that way. So I'm going to take this guy and solve for a. A equals negative c. Man, this... Come on. Come on. Thank you. There. So from here, I get that a equals to negative c, and then I'm just going to plug it in right in here. And so the a is a negative c. However, there is already another negative out there. Plus a b plus a c equals 0. So this becomes plus, so I get that b plus 2c must be 0. Good. And so I can combine this equation along with this equation, that b plus 2c, not plus 2c, minus 2c, minus 2c equals to 4, and if I add them together, I get that 2b, these guys cancel, must be equal to 4. So b must be equal to 4 divided by 2, or b must be equal to 2. Okay, one down. 2 more to go. Once I find the value of b, then I can go to this equation and find c. I get that we have b minus 2c. 2c equals 4, and the b is actually equal to 2, minus 2c equals 4. So minus 2c, if I subtract 2 from each side, must be equal to 2. Minus 2 minus 2. And then if I divide, I get that c must be equal to 2 divided by negative 2, or c must be equal to negative 1. That's 2 down, 1 to go. And I get that a from up here, that a was equal to negative c. A is equal to negative c, where the c is a negative 1. So a must be equal to positive 1. Good. All right, so that was a whole lot of work. Come back over here and say that this guy must be positive 1, this guy must be negative 1, and that the b is a 2. Any questions, any questions, any questions? Okay, and all of that was just part of this part where we were breaking that down, right? So it's a huge problem. Let's go back to basics over here, because we kind of lost track of what we were doing. So we started off with this ugly rational function. A good first step is always just to factor the denominator and have that in your pocket. Okay, but we did notice that the degree of the numerator was larger than the degree of the denominator. So we were able to do polynomial division to break it up into this. So this is here, x plus 1 plus the remainder of 4x over the divisor. Okay. Now that divisor is factorable this way, so we just replace this with that. And then we just did a whole bunch of work to figure out that this fraction can actually be separated into the summation of these three fractions with these constants. Okay, so this whole thing is going to end up being x plus 1 plus 1 over x minus 1 plus 2 over x minus 1 squared minus 1 over x plus 1. Good. Okay, I'm going to need to come back over here to restate the whole thing because it's getting really ugly. So let's restate the original question. So I already lost track of things. So okay, so I need the integral of, and this is going to be equal to x to the power of 4, x to the power of 4 minus 2x squared, plus 4x plus 1, that whole thing, divided by x to the power of 3 minus x squared minus x plus 1 dx. We're like, okay, that's too complicated, too ugly. We did a whole bunch of work, and we said, okay, well, we'd rather work with this guy. It's going to be the integral of x plus 1 plus 1 over x minus 1 plus 2 over x minus 1 squared minus 1 over x plus 1. I think I got that right. And that's just from up here. That whole thing is dx. So we can just focus on that. Okay, so it was a whole lot of work to go from here to here, and then that's where the payoff comes in, because this turns into several easy integrals, right? This is then going to be broken out into the integral of x dx, that's easy, plus the integral of just dx, that's easy, plus the integral of 1 over x minus 1 dx, that's easy, plus 2 integral of 1 over x minus 1 squared dx minus the integral of 1 over x plus 1 dx. Okay, so this is going to be equal to 1/2 x squared. Takes care of that one. Guessing and checking, the derivative of this is going to be equal to, bring down the 2, that cancels with a half, the power of 1, okay, plus x, takes care of that guy, plus ln of x minus 1, takes care of that guy, plus, what's this guy going to be? This is going to be, let's bring down to the 2. If we think of this as, x minus 1 to the power of -2, right, bring it up to the numerator, then this is going to be equal to, then this is going to be equal to x minus 1 to the power of -1, x minus 1 to the power of -1, and then there's an extra minus that happens here, so we have to throw in an extra minus. Right, -1 times -1 gets +1. To the power of this -1 gives you -2. Good. Okay. Minus, and then we have ln of x plus 1. Okay, so let's try and simplify these just a little bit. Not that there's much to simplify, it's just pretty ugly. We have 1/2 x squared. Let's move this guy out in front. So then we have plus x minus 2 over x minus 1. That takes care of this thing. And then I still have a plus ln of absolute value of x minus 1 minus ln of absolute value of x plus 1. And again, we can combine these two things together and end up with 1/2 x squared plus x minus 2 over x minus 1 plus ln of giant absolute value x minus 1 over x plus 1 plus a constant. No questions, no questions, no questions? Let's see if Doctor agrees. Okay, so because the polynomial in the numerator has a degree that's higher than the polynomial in the denominator, that's our clue to do long division, polynomial long division. After you do long division, it turns into this. Good. And then we factor the denominator. Once we factor the denominator, we know that the denominator turns into this. Good. So then we can do partial fraction decomposition to be able to break it up into this. Find the values of a, b, and c. Again, you can also use the method of choosing the perfect values of x. Could be a -1, that's helpful. +1, that's helpful. Sometimes 0 is always a good thing to check. So try different things and find the values that are missing. Good. Or do the systems of equations. Okay, either way, we end up with this ugly thing to integrate, which breaks up into individual things that are not so bad. And then we can simplify it a little bit, and that's how we get to our answer. Okay, case number 3 is the case where when we try and factor the denominator, we run into an irreducible quadratic factors, right? So it's a quadratic that cannot be further reduced into a product of binomials, linear binomials, because of the terms, right? It might lead into imaginary values. So, for example, x squared minus 1 factors into x plus 1 times x minus 1. However, x squared plus 1, right, doesn't factor into real value, doesn't have any real roots. This turns into x minus I times x plus I, right? It leads into imaginary values, right? Okay, so we want to stay away from the imaginaries for now, so we don't want to worry about that now. So for us, if we run into a quadratic that can only factor by going into the imaginary world, then we leave it alone. So this is an irreducible quadratic. It cannot factor any further unless you allow the possibility of imaginaries, and we don't want to do that. Okay, when we run into a term like that, a quadratic in the denominator, it's very similar to before, except now the numerator is not going to be a constant. The numerator is going to be a linear factor. It's going to be of the form ax plus b, where a and b are the constants that we need to find. Good. And if that quadratic is repeated, then we follow the same rule that we just saw, that we have to provide a separate fraction for each term, counting up to the power observed in the rational function given to us. Good. So here's an example. Let's say you're given this nasty looking rational function and you want to break this up. We have a linear, we have a quadratic, we have another quadratic. Right? So this will merit its own fraction with a constant out in front. This will merit its own fraction with a linear up in the numerator. And then finally this will merit its own denominator or its own fraction with it in the denominator. And again, instead of just having a constant, there's a linear equation that we need to solve for up in the numerator this way. Good. So we would do a bunch of work to be able to figure out the values of A, B, C, D, and E. That in itself is going to be really hard. That's really the hardest part of all of this. So find the values of A, B, C, D, and once we do that, the hope is that now that means that it's something that's easily it's easy to integrate, hopefully. We are optimistic because in this case, if we let a U substitution happen, then if we let a U substitution happen here, then there might be the perfect term up there with a power of x to the power of 1. Good. Or it might look like one of our well-known integrals at this point, such as this. The integral of x squared plus a squared dx is 1 over a tan inverse of x over a. Right? So this is something we just, a formula we should already know. Back from when reverse engineering this, what is the derivative of tan inverse? Right? So hopefully back in calculus 1 you remember how to do that. If we have some function theta equal to tangent inverse of, well, let's just forget the constant a. Well, that's fine. X over a, like that. And you want to find the derivative. Find derivative. Man, my computer's dying. Derivative. Then we bring this over and do tangent of theta equals to x over a, and now we proceed. Find the derivative, and then we'll be able to figure it out from there. And that's how you were able to figure this out. Okay, so if you don't remember that, go back to calculus 1 and try and find this in your notes. But it's just one of the standard ones we know for now. So it's on that list, right at the very, very beginning up here. I just gave you a list of like the known integrals for us at this point. So you don't have to justify any of these. You can just know them. So here it is, 1 over x squared plus 1 is equal to this one. And okay, they're presenting it in more general form where we have a constant a, right? So if this is an a squared. Okay. Okay, so let's look at this example. 4x squared minus 3x plus 2. Okay, so first of all, what we want to do is divide these. We use polynomial long division because they have the same term. So let's begin with that and see how that leads us. So we have 4x squared minus 4x plus 3. And we want to divide that into 4x squared minus 3x plus 2. Come on. And all the terms are represented, since this is the power of 1, power of 2, no power. Power of 2, power of 1, no power. Okay, so let's make them be identical, and these are already identical, so let's put a 1 there. So 1 times this is going to be 4x squared minus 4x plus 3. Distribute a negative 1 and add. Negative 1 and add down. Cancel this. Minus 1 makes it plus. Plus 4x minus 3 gives you just positive x. And then minus 3 plus 2 gives you a minus 1. Okay, so we're already getting making this a little nicer. So we have 4x to the power of 2 minus 3x plus 2 divided by 4x squared minus 4x plus 3 is actually equal to 1 plus x minus 1 all over 4x squared minus 4x plus 3. Okay, so we're getting a little closer. Now we got to figure out what to do with this guy. So we try and factor it, right? Try and figure out some way to factor this guy. You might try guessing and checking for a little bit, seeing what happens. But since this is the example where it doesn't seem to reduce easily, I'm going to guess it doesn't. So if we think about our quadratic formula, remember we have our quadratic formula of negative b plus or minus the square root of b squared minus 4ac all over 2a. So in the quadratic formula, if this is negative, come on, negative. If negative, then we have imaginary solutions. So it's pretty easy to just check if this is going to turn out to be something involving imaginary solutions. I have 4x squared minus 4x plus 3. So for us, the role of, remember this is based on the idea that the quadratic is this, x squared plus bx plus c. So the role of a is being played by a 4. The role of b is being played by a negative 4. Make sure we keep the sign. And the role of c is being played by a 3. So the b squared part, we have b squared minus 4ac. So this is going to end up being negative 4 squared minus 4 times 4 times 3. This is going to be 16. This is going to be 16 minus 16 times 3 is going to be 48. Right? So this is negative 32. Right? Negative. So I know that when this factors, it's going to have imaginary constants. The zeros are complex, right? They're imaginary numbers. So it doesn't factor any further. You want to leave it like that. Oops. You want to leave it like that. And now in order to do my partial fraction decomposition, I know that it's going to be equivalent to, well, I wonder why. Well, I mean, it doesn't factor any further, right? Since it's this first term by itself. What did I do wrong here? Can it possibly be this easy? They don't give you easy ones. What did I do wrong? No, that looks right. Okay. Right, so this is just going to be a u substitution that solves this now. Okay. Right, so we have our integral, and we have 4x squared minus 3x plus 2 all over 4x squared minus 4x plus 3 dx. So we know that this guy is going to be equivalent to 1 plus x minus 1 all over 4x squared minus 4x plus 3, right? And thanks to my work over here, I know that this doesn't factor any further without slipping into the imaginary number side, complex numbers, which we don't want to do. Okay, so we've at least managed to change it from this ugly thing into this guy. And then let's try some other techniques here. Let's see. So this is just going to be the integral of dx plus the integral of this thing, x and if we do a u substitution, we'll get this minus 1 over 4x squared minus 4x plus 3 dx. Okay, so let's do a u substitution to figure this out. So let's let u equal the denominator, 4x squared minus 4x plus 3. And so therefore du dx, come on, dx is going to be equal to 8x minus 4. And so du is going to be equal to 8x minus 4 times dx. So I almost have what I want here, but not quite. So close, right? Let's see. This one. Okay, no, this isn't working out. Let's try something. If we complete the square on these two terms and write it in terms of something squared plus 3, or plus something, so okay, so over here. Let's work with this guy, and we have 4x squared minus 4x plus 3. So I want to figure out what's the perfect thing to add, and if you remember complete the square, it's going to be this little formula. It's the constant in front of the x. We multiply that times a half. Half of that squared will be the perfect thing to add and subtract. Half of that will be equal to negative 2 squared, which gives you a 4. So that's what we want to do. We want to add a 4, subtract a 4. Hopefully that gives us the perfect thing to add and subtract. Also, I guess we could have factored out a 4 from there. Let's do a 4, and then we end up with x squared minus x. Half of that squared. So then from here we end up with 1/2 of the minus 1 squared, which then equals to negative 1/2 squared, which equals to 1/4. Okay, so this has a plus 3 here, and we're gonna have a 4 parentheses x squared minus x plus 1/4 minus 1/4 plus 3. That guarantees that these two become a perfect square trinomial, which gives you an x minus 1/2 squared, right? From there, that's how I get the minus 1/2. Minus 1/4. The whole thing is still multiplied by the 4, and there's still a plus 3. So we get 4x minus 1/2 squared minus 1 plus 3. And we can always rewrite the 4 as a 2 squared. X minus 1/2 squared minus plus 2 now, combining these two. And so I'm going to distribute that 2 in there, and I end up with 2x minus 1 squared plus 2. Good. Questions, 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 questions? Okay, so once I have that, I can rewrite this the following way. All right, so back to this. So I tried this and it was close, but there's just some ugly constants that bug me. So we want to say this is equal to dx plus the integral of x minus 1 over 4x squared minus 4x plus 3 dx. And so I'll just copy that back there again. Okay, so now the denominator, we saw that turns into 2x minus 1 squared plus 2. That's the denominator. And then there's this 2x minus 1 up here. Okay, x minus 1 up here. So let's figure out a way to rewrite it with a 2x minus 1. So if I had a 2x minus 1, and then I multiplied it by a half, that would give me x minus a half, and I need another minus a half. All right. If I distribute this, I end up with x minus a half, and then minus a half gets you to minus 1. Minus a half gets you to minus 1. Something is off. So this is going to be dx, right? So let's put a 1 there, plus integral of that, integral of that. There's something off here. Does it have a okay, that's fine, I guess. I think that's right. Okay, so then I can factor out the half. And so I can do a u substitution. And then the u substitution, okay, so let's let u equal to 2x minus 1. So that I end up with u squared plus 2, and there's a u there. And its derivative, du, come on, du dx is equal to just 2. So du is equal to 2 dx. Okay, so let's see, that means that there's going to be an extra 2 that's needed there. We're going to balance it out with an extra 1/2 out there, so that this part right here is my du. Okay, so let's see if we make this work. This will be the integral of dx plus, there's a 1/2 out there, come on, 1/2, integral of, and then there's a 1/2, and I intentionally rewrote this part so that it has a 2x minus 1, so it'd be a 1/2 u minus a half all over u squared plus 2 du. I can factor out another half, and I end up with integral dx plus 1/2 times another 1/2 when I factor out these. Factor out this 1/2 and this 1/2. I'll end up with another term of a half here. Integral of, and it's u minus 1 all over u squared plus 2 du. And then if I separate these, I should have integral dx plus 1/4 integral of u over u squared plus 2 du plus 1/4 integral of minus 1 over u squared plus 2 du. Okay. So here we're going to do, you can do like a u substitution here to get this this thing guy to work out. So let's say we let w equal to u squared. Come on. It doesn't want to erase that. So we'll let that equal to u squared plus 2, and therefore our dw du is going to be 2u. So dw equals to 2u du. Good. So u du, there's just an extra term of 2 that's missing, so put a 2 there, 2u du, so we have to balance it out with another 2 out there. Good. And this guy we're just going to pull out the minus out in front. Almost there. Integral of dx plus 1/8, and then it'll be the integral of 1 over w dw plus, minus 1/4 integral of 1 over u squared plus 2 du. Good. Okay, so this guy should just be equal to x plus 1/8 ln of w minus 1/4, and this should be our tan inverse function. Okay. So, 1/8 ln of that guy. Okay, and then 1/4. Yep. And this is just going to be tangent inverse of u. Right, so this is going to be tangent inverse of u over root 2. And there's an extra 1 over root 2 that happens there. Right, and that's because the general one that we have is this. It's the integral of 1 over x squared plus a squared dx is equal to 1 over a tangent inverse of x over a. Right, that's the way it looks. I think it was in the... This is one of the ones that was up here. There it is. 1 over a tan inverse of x over a plus a constant, right? When it fits this form. All right, so 1 over a right, so it fits that form. So for us, this is just equal to u squared plus 2. We're just rewriting this as 1 over u squared plus root 2 squared. And so the a is a root 2. Come on, computer. Root 2. Good, that's how we get that. And we're almost done. Now let's do some substitution here. The w was actually equal to u squared plus 2. So let's rewrite that. This is going to be equal to x plus 1/8 ln of w squared plus 2. w squared plus 2, absolute value, minus 1 over 4 times root 2, and we can write that 4 as a 2 squared, and then we'll combine those two in a second, and then this is tan inverse of the u over root 2. Okay, we're almost done. Now the u, come back way over here. Where was the u? The u came in when we did this. U was equal to 2x minus 1. It is equal to 2x minus 1. So this is going to be x plus 1/8 ln of 2x minus 1 squared plus 2, absolute values, minus, and now this is 2 to the 1/2, 2 squared times 2 to the 1/2, combining like terms, we get 2 to the power of 2 to the power of 2 plus 1/2, which is equal to 2 to the 5 over 2. Okay. So this becomes 1 over 2 to the power of 5 over 2 power. Tangent inverse of 2x minus 1 all over root 2 plus a constant. Let's see, is that right? Right answer. X 1/8 ln of, and if we FOIL that out, we end up with 4x squared plus 4x plus 4x plus 1 plus 3 gives you this thing, that gives you that, and then that gives you that, plus a constant. Yep, that's the answer. Man, that was ugly. Let's see if we can walk through the whole thing. Oh man, I hate that. Why does it not like boxing anymore? Man. I hate computers. Okay, so now this weird ugly box won't go away. Just to add to the ugliness of this. Wow, that was a long problem. Okay, so this was the original question here. We did long division, polynomial long division to simplify it, and we got it to this here, 1 plus this, right? And then we recognized that we couldn't factor this any further by using the quadratic formula. We can figure out that was going to be negative, so we couldn't factor it any further. So we rewrote it this way. And now I tried to do a quick little U substitution. I thought it was going to be, had a suspicion it was going to be a much easier question, but it wasn't quite there because the constants weren't there, right? If I had been lucky and this had been a nice linear equivalent of that, so maybe 8x minus 4 there, then it would have worked out in a much nicer way. But it didn't quite work out. So another little trick that you can try is to complete the square on this guy, which is what we did. Came over here, tried doing complete the square, factored out the 4, stuck in to here the perfect value, and that perfect value is equal to 1/2 this constant squared. Right? Hopefully you remember how to complete the square. Then these turn into that. Right, distributed, combined like terms, and I ended up with this. We would have ended up with the same thing if I stuck with this before factoring the 4. We would have gotten the same result. After we did complete the square, I ended up with a 2x minus 1 squared plus 2 in the denominator. So I just thought of some clever way of rewriting the numerator in terms of a 2x minus 1. I knew I could do that because they're both power of 1. And the reason I do that is because then it'll make it easy for me to do a U substitution and rewrite the whole thing in terms of U. So then that gave me this thing here, and that's supposed to be a 1/2 U minus 1/2. Good. Okay, and then once I have that, then I can factor out the 1/2. I can separate these into 2 separate fractions, this denominator under the U, this denominator under the minus 1. Good. Okay, and then for this one, we do one more substitution. I'm calling it a W substitution, which would then give me a nice straightforward integral in terms of W. So then I get ln of W, keeping track of the constants out in front. And then we have to reintroduce everything. So the W in terms of U, and then the U in terms of X. So we can get back to our final answer. Finally, that little box works. So we can get back to our final answer in terms of X with a constant out here. Good. So this one was, what was the original question? 4x. So this is the integral of, and we had 4x squared minus 3x plus 2 divided by 4x squared minus 4x, 4x squared minus 4x plus 3 dx. And that's our answer. It is not a nightmare. They really are this bad. Welcome to calculus. They get hard. right? So you gotta just chip away at them slowly and be really meticulous with things. Try and be neat and organized, and that's one thing I really hate about this COVID times. It's really hard to be neat and organized on my laptop this way, so I apologize for that. It is an ugly mess. If we were in the classroom, I think I could do a much better job of making it nice and neat and organized and taking advantage of all the boards we have in the rooms. But this would be one of those like 3D solutions where I would work on the boards starting on one wall and go to another wall and go to another wall, and the answer would just completely surround you in 3 dimensions all around the room, and it would be easier to see the whole thing from start to end. But unfortunately we have this. And now this thing is stuck there. Man, this computer program is not happy. All right, we'll just leave it there. Good. Any questions? No. Okay, this is a good place to stop for now, and we'll pick up on Thursday. If you have any trouble with any homework, let me know. Send me an email with suggestions on whatever homework problem you're having issue with, and maybe that's something we can do. Okay. All right. If there's no more questions, we'll stop here. Keep chipping away at that homework. Should be really ready to do up through 7.5. 7.5 doesn't really have anything new either, I don't think. It's just sort of a summary of all the various techniques we've learned so far. But I don't think they have any new material in there. So you should be able to do the first 5 sections of Chapter 5 at this point. Okay? Or at least attempt them. Questions?